Welcome to Chem 1A. This is Chapter 2, Atoms, Molecules, and Ions, Part 1 Screencast. The substances that make up our world can be classified in a number of different ways, and one of the ways of classification is shown as follows. If we start with matter, all the stuff that makes up our universe, and we look at a specific piece of matter, a specific chunk of matter, we can ask some questions about it. For example, we can ask whether that chunk of matter has constant properties and composition throughout it. And if the answer is yes, the properties and composition are constant throughout, then we have what's known as a pure substance. If we do not find constant properties and composition throughout, then we have what's known as a mixture. Now, for the pure substance, we can ask the question whether or not that substance can be simplified by chemical means. And if we can simplify it chemically, then we have what's known as a compound. For example, sodium chloride or table salt is something that is made up of the elements sodium and chlorine, and it turns out there is a way to, using chemical methods, break that down into simpler substances, in other words, the sodium and the chlorine. Water can similarly be broken down into simpler substances, hydrogen and oxygen. So those are examples of compounds. Now, some substances can't be simplified chemically, and those are, of course, the chemical elements. They're already as simple as they can be. Carbon, can't simplify it any further by chemical means. Hydrogen, it's already as simple as it gets. Sodium, as simple as it can be by chemical means at least. So those are the elements. Now for mixtures, we can also ask some questions. And for a mixture, one of the key questions is whether or not it's uniform throughout. And if it is uniform throughout, then we have what's known as a homogeneous mixture. Whereas if it's not uniform throughout, then the mixture is called heterogeneous. Note that homo means same. Homo is a prefix. And so a homogeneous mixture is something that looks the same throughout. For example, a glass of Gatorade, it's going to look the same at the top and the bottom or any place you look, whereas something like a pizza is going to look pretty different whether you're looking at a piece that has mostly pepperoni or a piece where there's a mushroom or a cheesy piece. And so heterogeneous, or hetero means different, is a mixture that doesn't look the same throughout. Now, recall that what scientists do is they measure things, they do experiments, they collect data, and then they formulate hypotheses, and then they try to put all of this stuff together to make some laws or principles or theories, which are essentially ways to understand how the universe works. And so we've developed an atomic theory, which we're going to look at today. You may have heard of plate tectonics. There's Darwin's theory of evolution. We have gas laws. We have thermochemistry or thermal laws, and we know things about electricity and laws relating the relationship between, say, voltage and current and resistance. And so these are all ways that we've figured out to understand how the universe works. Well, we're going to look at do a little bit of this ourselves, and we're going to look at what both previous scientists have done and try to analyze what their results mean. Okay, well, let's start with this. You might look at this substance and say, kind of shiny, kind of silvery colored. It's probably a metal, and in fact it is. It's the metal magnesium. And if you took a piece of magnesium and held it in a candle or a Bunsen burner or put a match to it, this is what you'd see. It would burn very, very brightly, so brightly in fact that you wouldn't want to look at it directly, and you'd see sort of a white powdery smoke kind of thing coming off of it. Well, what happens is magnesium, of course, is reacting with oxygen from the air. In other words, it's burning. And if you start with magnesium and oxygen, the substance that's formed has to contain magnesium and oxygen, and it is in fact magnesium oxide, and that is that sort of white powdery stuff that if we do the burning carefully in, let's say, evaporating dish, we get this white powdery substance, magnesium oxide, and we can actually collect it if we're careful. Okay, now if we do this experiment carefully and measure our results, we find something like the following. If we have 1.157 grams of magnesium and it reacts with 0.762 grams of oxygen, we end up collecting magnesium oxide, and we end up collecting 1.919 grams of that. Now you might notice something, and this probably isn't that surprising. The total mass of the magnesium and oxygen as individual elements when we start is 1.919 grams. The sum total of our product, magnesium oxide, is also 1.919 grams, and so the amount or mass of substances we started with and the amount or mass of substance we end up with are in fact the same. And this is a generally true fact. Whenever we do a reaction, the starting stuff, which we call the reactants, and the ending stuff, which we call the products, these two have equal masses. And since this is such a universally established fact or truth in science, we have a relationship that is called the law of conservation of mass that summarizes this. And the law of conservation of mass basically says when any chemical reaction occurs, the mass of the products and the mass of the reactants are equal to each other. Now we also find some other things that might be not quite as obvious perhaps. For example, the magnesium oxide that was formed, whether we have a small amount of magnesium oxide or a large amount of magnesium oxide, the magnesium and oxygen are always in a ratio of 1.52 to 1 by mass. And in other words, we'd have 1.52 grams of magnesium for every 1 gram of oxygen, for example. The reason for this is because magnesium oxide contains 1 magnesium and 1 oxygen, and a magnesium atom weighs 1.52 times more than an oxygen atom. So whether we have 1 of each, 100 of each, 1,000 of each, any number, the magnesium and oxygen numbers will always be the same in terms of how many of each we have, but their mass will always have a ratio of 1.52 to 1 magnesium to oxygen because of the difference in mass between magnesium and oxygen atoms individually. This is also true in general. The numbers will vary, but the concept is the same. For every sample of water, for example, we have a ratio of 1 to 8 by mass, and the reason is that oxygen is 16 times heavier or more massive than hydrogen, but there are 2 hydrogen atoms for every 1 oxygen atom. So we have essentially a 16 to 2, or which reduces to 8 to 1 ratio by mass for oxygen to hydrogen in any sample of water, no matter how much you have. Another compound, similar idea, the compound octane, C8H18, always has carbon and hydrogen in a ratio of 5.33 to 1 by mass. And in general, how we summarize this as a law is that any sample of a specific compound is always going to have the same proportion of elements by mass, and we call this the law of definite proportions. The proportions are fixed or definite for any compound. Now, one other thing to note is that elements can sometimes form different compounds with the same elements. Carbon and hydrogen is a classic example of this. Carbon and hydrogen can literally make millions of different compounds, and here are a few of the simplest. Methane, CH4, 1 carbon to every 4 hydrogens. Propane, C3H8, 3 carbons to 8 hydrogens. Butane, 4 to 10, and octane, 8 to 18. And then notice, since the carbon to hydrogen ratios are different in each compound, so will be the mass ratios. Methane has a 3-to-1 ratio of mass carbon to hydrogen, propane 4.5 to 1, butane 4.8 to 1, and octane 5.33 to 1. Now let's look at a simpler example for the next principle, and that is a pair of compounds formed by copper and chlorine. Copper and chlorine can form a green solid that has a mass ratio of 0.588 grams of chlorine for every 1 gram of copper, and it can also form a sort of aqua blue or teal colored solid with a mass ratio of 1.66 grams of chlorine for every gram of copper. Now, you might look at those ratios and say a couple things. One is, why do we care? And another is, those ratios, they don't look very nice. They're not 2-to-1 or 3-to-2 or something like that. But if we do a ratio of the ratios, we get something sort of interesting. If we make a ratio of the aqua-colored compound to the green-colored compound, and we do their mass ratios, the aqua-colored compound was 1.116 grams of chlorine per gram of copper. The green compound was 0.588 grams of chlorine per gram of copper. And then if we simplify this ratio of ratios, notice that grams of copper will cancel. Grams of chlorine, the units at least, will cancel. And then some of you observant folks might have noticed that 1.116 is exactly twice 0.588. So this actually simplifies to a 2-to-1 ratio. And this type of thing happens on a regular basis when we're dealing with compounds where there's different compounds that can form from the same, in this case, pair of elements. And what we find in this specific case is that the aqua blue compound has twice as much chlorine as the green compound for the given amount of copper. So here's a visual representation of it. And if we have twice as much chlorine per copper in this compound compared to that one, how should we interpret it? Well, here's one way to think of it. For every copper, so if this sort of copper-colored atom represents, or sphere represents an atom of copper, then if this one has, let's say, 1 chlorine, how many should this one have? And hopefully you'd say it should have twice as many. So maybe this is going to suggest something, that the compound, the green one, is 1 copper to 1 chlorine, and the aqua compound is maybe 1 copper to 2 chlorines. And in fact, that is the case. So it's pretty reasonable to propose that both copper and chlorine are made up of small units. You probably already know that those small units are atoms, and these units have different mass than the copper atoms or copper units have different mass than the chlorine units, and that the aqua compound must have twice as many chlorines per copper as the green compound. And if we now go back to the substances and write chemical formulas, then the green compound might be CuCl, and the aqua compound might be CuCl2. And in fact, that is what their formulas are. Now, this is also a law. It generalizes when we are dealing with other situations where there's several elements that can combine to make different compounds. And this is called the law of multiple proportions. And it states that elements can combine in different ways to form different substances, but the mass ratios are going to be small whole number multiples of each other. In other words, for the previous one, it was a 2-to-1 ratio of their mass ratios. In other cases, it might be a 3-to-2 or a 4-to-5 or some other small whole number ratio.